What is up? We are jumping forward just a little bit. Last time we talked about what a vector field looks like, right? So in 3 dimensions, a vector field might look something like this, right? So it could be maybe 2x times I plus 3y times j plus x plus y plus zk, right? Maybe something that looks like that, where you plug in a 3-dimensional point and out pops a 3-dimensional vector, and that vector tells you the direction you have to be going in, type of thing. Okay. All right. So what we're going to do next is take this idea, and now that we have an idea of what a vector field is, we're going to look at 2 different operations that we can do on vector fields. Right? So today we're just going to worry about how to actually use these things, and then we'll worry about applications later on. But let's worry about just what they're called, how they're defined, and how we can actually find these particular operations. All right. So the 2 operations are called curl and divergence. Okay. So we're just going to go through these, both of them. The second one, actually, curl is a little bit tougher, so the second one should be a little bit easier. These things are defined mostly, or at least they're mostly used with R3, right? In other words, 3-dimensional vectors. Okay, so thinking about that, let's give ourselves a 3-dimensional vector field. So let's let f, our vector field, be some function p, right, in the ith component, right, plus some function q in the jth component, and some function r in the kth component, right? Or if you want to write it out like this, you can think about it like that as well, where p, q, and r are functions, and this gives me a vector field in R3, right? So let's define what we're going to call the curl of f as follows, right? So let me write this out for you, then we'll see a couple of maybe easier ways to think about how to remember it. So let me write this thing out. Boom, there it is, right? So there's my curl of f, right? I know it looks kind of like a lot of really tricky notation, but once you get used to it, it's really not that bad. So let's just remind ourselves of what these notations mean. For instance, what about this dr over dy, right? Remember what that means is to take that function r, right, and then to find its partial derivative with respect to y, right? So that dq over dz, that means to take the function q and to find its partial with respect to z and so on, right? And then if we look at the i's, j's, and k's, remember those represent vector components, right? So it looks like what we're actually getting out of this, the result of this, is a vector, right? To where component I has the partial of r with respect to y minus the partial of q with respect to z. The jth component has the partial of p with respect to z minus the partial of r with respect to x. And then for the kth component, the third part, the partial of q with respect to x minus the partial of p with respect to y. Right? So I'm plugging in a vector field, right? In other words, I'm plugging in a 3-dimensional vector like this, and out pops another 3-dimensional vector. Okay, so let's think about maybe ways we can remember this formula a little bit easier. So let me clean up this workspace a tad. All right, and let me give you just a little bit more notation. Oops, sorry, I forgot to put my pen back on. So here's a little bit more notation for you. This upside down triangle thing, that's called the del, right? And the way we're going to define the del is this, right? It'll be the first component with the partial with respect to x, the second component with the partial with respect to y, third component partial with respect to z. Okay? So if I wrote out del f like this, right, then that would be the derivative of f with respect to x in the ith component, right? Oops, and then plus the derivative of f with respect to y in the jth component, and the derivative of f with respect to z in the kth component spot there. Okay. All right. Or if you like this again better as a vector, the derivative of f with respect to x, with respect to y, and with respect to z. Okay. So that is what we're going to call del f. Okay. And if you notice, some of these things might look a little familiar, especially when we look at that definition of curl up here. You might remember some of that stuff when we were doing cross products and whatnot. So let's see what happens, right? We've seen del, we've seen del f. What happens if I take del, right, this operation right here, this function right there, that vector that's going to pop out. What happens if I cross that with my vector field f, this thing up here? Okay. Well, if you remember the way we do this cross product, right, especially for these three-dimensional ones, right? So if I have I, J, and K on my top row, del will go across the middle row. So remember how we're doing del, the ith component is the derivative with respect to x, the jth component is the derivative with respect to y, and the kth component is the derivative with respect to z. Right? And then f is going to go along that bottom row where the ith component has the function p, jth component has the function q, and the kth component has the function r. Right? And if you actually carry out this cross product, right, and multiply it all together, what pops out is exactly this formula. Right? So it's just another way for us to think about the curl of f right here. You can either try to memorize that formula or hopefully just use it enough to where you're used to it. Or if you just kind of remember this picture and this setup, then you can actually take this, work it out, and that formula will pop out for you. Okay. All right. So one other thing this kind of points out to us as well, where when we were taking a vector field f and took the curl of f, a vector popped out. When I take the del crossed with f, I get another vector popping out. Right? All right. So yeah. So this thing again does return a three-dimensional vector. Okay. All right, so let's work through a couple of examples just to see how we can do some of these. And again, let me clean this up and keep some of this with us. All right, so consider this vector field f, right, where it's sine of yz in the ith component, sine of zx in the jth component, and sine of xy in the kth component. Let's just practice actually computing the curl. Right? So what is the curl of f going to look like? Right? Well, again, we could line it up in this cross product type of notation, right? To where we'll have d dx, d dy, d dz, and then the first function is sine of yz. Whoops, didn't give myself enough space here. This would be sine of zx, and then this would be sine of xy. Okay. All right. So I can sit there and compute that. Right? So if we looked at this thing, right, which is what we get when we actually calculated it, it would be the, let's see, how do I want to write this out? It's going to be the derivative, let me do this a long way first of all, the derivative with respect to y of r, right, which in this case, if we want to think about these things, there's p, there's q, and there's r, right? So it's the derivative with respect to y of sine of xy, right, minus the derivative with respect to z of q, right, where q is sine of zx, right. All of that goes with component I, right. So that's the first part, and then that's plus the derivative with respect to z of my function p, right, which is sine of yz, minus the function with respect to x of r, which is sine of xy, right? All of that goes with the jth component, and then the last component is this, the derivative with respect to x of q, which again is sine of zx, minus the derivative with respect to y of p, which is sine of yz. And that goes with the kth component. Okay. So if we write all this stuff out, right, if we go to this first one, the derivative of sine of xy with respect to y gives me a cosine of xy, right? And then the derivative of xy with respect to y is just another x, minus the derivative of sine of zx with respect to z gives me a cosine of zx, and then the derivative of zx with respect to z is an x. Right? So there's my ith component part. And then for the jth component, the derivative with respect to z of sine of yz gives me cosine of yz, and the derivative of yz with respect to z gives me a y. And then minus the derivative of sine of xy is cosine of xy, and then the inside part with respect to x gives me a y. That goes with j. And then for the last one here, the derivative with respect to x of sine of zx gives me cosine of zx times z, and then that's minus cosine of yz times z, and that goes with k. All right. And then we could do a couple of little things on here if we really wanted to, right? Like for instance here, I could maybe factor an x out and then have cosine of xy minus cosine of xz I. The second one, I could factor a y out and have cosine of yz minus cosine of xy with j. And then factor z out to get cosine of, excuse me, cosine of zx. And that's cosine of yz with k. And then we could also write this out in a vector form of x cosine of xy minus cosine of xz, y times cosine of yz minus cosine of xy, and then z times cosine of zx minus cosine of yz. All right, so that is the curl, right, of that function f. And we'll go through another example here in just a little bit, but let's keep on going and talk about a few more definitions, or at least a few more questions here. If you remember when we were doing cross products, if I had some three-dimensional vector A and crossed it with itself, I got 0 right back. Right? So what happens if I take the curl of del f? What's that going to give us? Right. Well, again, remember a curl is just a cross product here, so let's say I, j, and k. Right. This would be, again, the derivative with respect to x, the derivative with respect to y, derivative with respect to z. And then for del of f, remember this was the derivative of f with respect to x. This went to the derivative of f with respect to y. This went to the derivative of f with respect to z. Right? So that's what our setup could look like. So then if we actually carry out this cross product and multiply the whole thing out, we're going to get this. Right? So the first thing we're going to have is this little notation. It'll be d dy times df over dz. Right? Let's think about what these symbols mean. Remember, these d's represent the differentials. Right? So in the denominator, it's the differential of y and the differential of z. Right? So the partial of y and the partial of z. So what about this d times df thing? Right? This says to take the derivative, and that says take the derivative again of just my function f. So that's the second derivative with respect to f, or the second derivative of f. Right? So I'm taking two derivatives of f. I will either find the partial with respect to y and then the partial with respect to z, or if you remember, that's the same thing as partial of z and partial of y. Okay? All right, so when we go through this and multiply all these things together, here's what it's going to look like. All right, so it'll be the second derivative of f and dy dz minus the second derivative of f over dy dz, right? Because if you remember how we do this first one, it is this product minus this product, right? Which gives me this minus this. Okay? And then that's times I. Okay, so let me get rid of some of that stuff. So it's that times I. Okay? And then that's plus, if we do the second one, right, that means we'll take this and this, right, which would give me what, d2, oops, sorry, using the wrong color, sorry, my bad, d2f over dx dz minus d2f dx dz. J, and then if we did the same thing with the last one, I'd have the second partial of, or two derivatives of f with x and y minus the two derivatives of f with x and y. Right. Now, if you notice, those two things are the same thing. Those two things are the same thing. Those two things are the same thing. Right? So what this winds up being is just 0 times I plus 0 times j plus 0 times k, which of course is just 0. Right? Now be careful here. When we're writing out this 0, what does that 0 represent? Right? It's actually this three-dimensional vector 0, 0, 0. Right? It's not the scalar because it is still a vector. Okay? So the curl of del of f, what we just proved is that's always going to give me 0. Okay? And that leads us to this definition. Right? If f equals the del of f, then that vector field f is defined to be conservative. Right? Of course, another way to think about that is this. That means the curl of f is going to be 0. Right? And of course, all of this is assuming that these tons of partial derivatives that are popping out, we're assuming that every single one of them exists, right? If one of these partial derivatives doesn't exist, then all this stuff kind of gets blown up on us. Okay. All right. Let's do one more curl example, then we'll look on divergence. Right, so as a reminder, there is our definition for the curl. Let's use this particular vector field f. Let's see, and I guess let me write it like this. F of x, y, z gives me e to the xy times sine of z j plus y times arctangent of x over z k. Right? So in this case, there's nothing for I, so that component is 0. Right? So if you like to see it as a vector, here's what it would look like. Right? So let's calculate this del of f. Right? So it's again I, j, k, and then the partial with respect to x, partial with respect to y, partial with respect to z, and then the I component is 0, and then this has e to the xy sine of x, and this is y times arctangent of x over z. Okay. Right. So again, if we follow this along, right? So remember, this is my function p, q, and r up here in this particular definition of the curl. Right? It'll be the derivative of, and I didn't write that out well, r. It'll be the derivative of r with respect to y. Right? So that just gives me arctangent of x over z. Right? Minus the derivative of q with respect to z. And I'm just realizing I messed up just a little bit. I wrote down sine of z up top, but then I put x's right here. So those should be z's. Okay. So the derivative of q with respect to z, well, this e to the xy is a constant, and the derivative of sine of z gives me cosine of z. Right? And then that's times I, plus the derivative of p with respect to z, that's just 0. The derivative of r with respect to x, well, the y is a constant. And then if you remember, if I have arctangent of u, its derivative is 1 over 1 plus u squared du. So I'll have 1 over 1 plus x over z squared times, and if I have x over z, that's the same thing as x times 1 over z. And this partial with respect to x is just 1 over z. All right, and then that's times j. Okay, so let me clean up a little of this. And then the last one is going to be the derivative of q with respect to x. So if I have e to the xy, its derivative is e to the xy times y, and then that's times sine of z. Right? Minus the derivative of p with respect to y is just 0, and then that's times k. All right, so this just gives me this vector arctangent of x over z minus e to the xy cosine of z, negative y over z times 1 over 1 plus x over z squared, and then I get y e to the xy sine of z. And there's the curl. Okay. All right, so again, the notation is kind of confusing. It's easy to get it swapped around, so maybe just write it down on a note card, have it sitting right next to you when you're doing the homework, and maybe that'll help. Okay. All right, and I should have mentioned this before, but leave a little bit of space underneath the curl work because we're going to go back and kind of reference that when we do our divergence. Okay, so let me define for you the second operation, and it's a little bit easier. It's called the divergence. Right? So let's let f be some vector field. Right? So pi, qj, and rk. Right? Then the divergence of f is just the derivative of p with respect to x, the derivative of q with respect to y, and the derivative of r with respect to z. Right? Now, if you notice, I don't have any i's, j's, and k's in here, so this thing actually returns a scalar. Right? I mean, the scalar might be a number, could be some x's and y's in there, but it's not a vector. Well, I guess it's a one-dimensional vector, but it's not a three-dimensional vector anymore. Okay? And one way that might help you think about this is if you remember, the del was this, right? The derivative with respect to x, derivative with respect to y, derivative with respect to z. Right? So it looks like that the divergence of f is just the same thing as the del and the dot product with f. Right? Because if I take this and I dot product it with p, q, and r, we get the derivative of p with respect to x, whoops, not a vector anymore, plus the derivative of q with respect to y, and the derivative of r with respect to z. Right? So if that helps you remember the formula for the divergence of f, have at it and use that. Okay. All right. So let's look at our first example where I had this vector field f of sine of yz, sine of zx, and sine of xy. Right? What's the divergence of f look like here? Right? Well, it's this first part, it's this derivative with respect to x. So it's the derivative of that of sine of yz, plus the derivative with respect to y of the second component, plus the derivative with respect to z of that third component. Okay. Now, if you look at this first one right here, there are no x's in it, so those things are all constants, so its derivative is 0. If you look at this one, it has no y's in it, so its derivative is 0. And this one has no z's in it, so its derivative happens to be 0. Right? So this is actually a special case. This will happen every now and then, not too often, but it'll happen every now and then. If you take the divergence of a function f and you get 0, then f is said to be incompressible. Right? And these things actually come into play, at least these words might make a lot more sense when we start talking about the fluid dynamics and E&M type of a stuff associated with it as well. Okay? All right, let's look at our second example. and see what we can do for that divergence. Right? So for the second example, I gave you this vector field of 0, e to the xy sine of z, and then y times arctangent of x over z. Right? So the divergence of f is again the derivative with respect to x of that first component plus the derivative with respect to y of the second component and the derivative with respect to z of this third component. Right. First one's not bad. That derivative is just 0. The second one, let's see, sine of z is just a constant, so what's my derivative of e to the xy? Well, if I have e to the u, its derivative is just e to the u times du. Okay? And then I've got this constant sine of z right here. Plus, and then this one, let's see, y is a constant, and then I've got z's inside arctangent. So if you remember again, arctangent of u has a derivative of 1 over 1 plus u squared du. So this will be 1 over 1 plus x over z squared. Right? And then if I have x over z, what's its derivative with respect to z? Well, that's the same thing as x times z to the minus 1, so I'll leave that x alone. And the derivative of z to the minus 1 is negative 1, z to the minus 2. So it looks like it's a negative x over z squared. So let me put that up here as well. Okay. And then if you notice again, that's not a vector anymore. It is just a scalar. Right? So again, the divergence of f returns a scalar. Okay. So I guess that kind of asks this question: what happens if we combine these things together? Right? What's the divergence of the curl of f going to be equal to? Well, there's a little proof in the book, and it's a lot like the one we did before where we wrote out all those different differentials and added them all up to see what we got. In this case, it does actually wind up to be 0 again. All right, so here's your assignment. All right. This is section 13.5. Right. Look at 1, 3, 5, and 7, the odds. Right. And then look at 10, 11, and 13. Right? So some of these are just straight up computations. Some of them make you check to see if you actually have something which makes sense. Like remember when we talked about A cross B cross C, is that going to be defined? Well, this returns a vector, so we can cross it with that. Or what if I had like A cross B dot C? Is that going to be defined? Some similar stuff like that with number 10 you have to mess around with. Right? So that's it. That's our introduction to the curl and divergence. Hope you enjoyed it. I'll catch up with you later. Bye.